Okay, let's look at page 2 of quiz number 6 from General Chemistry 1 from fall of 2018. So question number 5 is asking about molarity. It says to calculate the molarity of a solution, and it gives us the information that we need there. So remember with molarity, we are always, right, anytime we're looking at molarity or concentration, right, molarity or concentration pretty much means the same thing here for us. We're looking for moles of whatever per liters of solution. Right, so moles of the substance per liters of solution. So we're given units of grams. So we need to, convert the 5 grams into moles, and we're given units of milliliters, right? So we need to convert milliliters into liters, right? So we're going to do our 2 steps there, the red step and the purple step. Now, grams to moles should be a very familiar conversion for you at this point. Hopefully you got that kind of locked down at this point, but let's convert grams into moles. So we got 5 grams of glucose. There's 180.15 grams for every 1 mole of glucose. And if we do that math, I got it to be about 0.0278 moles of glucose. Oops, make that a little bit clearer. There it is. Okay. Converting milliliters into liters. Right. I'll just quickly knock this out here, right? We have 100 milliliters. For every 1,000 milliliters, we have 1 liter, right? So if we do that math, we get 0.1 liters. So I can take my value here, divided by 0.1 liters, and I get my answer to be 0.278 molar, right? So 0.278 molar solution. So easy peasy in this case, right? Convert grams into moles, convert milliliters into liters, divide one by the other. Now question 6 is asking about what happens once we make a solution, right? So it says, what is the molar concentration of each ion present in a solution of calcium nitrate? So calcium nitrate, right? That's calcium nitrate. We need to know the chemical formula for this. Now, calcium nitrate is an ionic compound, right? And if we take a look at our solubility rules, the solubility rules state that compounds containing nitrates tend to be soluble. And so when calcium nitrate is put into solution, aka when you dissolve calcium nitrate, it dissolves into calcium 2 plus and 2 nitrates. And we're going to need to know, let's say, this balanced equation here to be able to answer this question. Because here's how this is going to work, right? We need to figure out how much calcium is in solution and how much nitrate is in solution. So we need to know the ratios, right? We need to know our balanced equation, so to speak. Here's how this is going to look. If we start out with 0.025 molar calcium nitrate, for every 1 mole calcium nitrate, I have 1 mole of calcium 2 plus, which means that, let me switch to green here, which means that in solution I have a 0.025 molar solution of calcium ions. Now you might be saying, well, hold on a minute here, right? Your units don't quite cancel out with each other. Well, remember what we just said in question number 5 about what molarity is. Let me go back here, and just for argument's sake, let's take a look at this issue of units here. Because right now, right, I've got molarity here and moles down here. Remember, we typically want to cancel our units out, but molarity doesn't cancel with moles, right? So I'm going to take this exact same equation and just kind of rewrite it. So all I'm going to do is take this right here. I'm going to slide it over to give myself some space. What are the units for molarity? Well, it's moles, right, per liter. Aha, okay. Now, as soon as I make this subtle change, right, now my units can cancel. Moles of calcium nitrate. Ooh, sorry about that. I don't know what just happened. Moles of calcium nitrate cancels out with moles of calcium nitrate. And then we're left with units of moles of calcium per liter. So let me just get rid of that so you guys can see the units here as we have them. Okay? So we converted molarity, right? Molarity of the solution into molarity of the individual ion. And we're going to do the exact same thing for nitrate, right? So we have 0.025 molar calcium nitrate. Looks like I'm going to run out of room, unfortunately, here. So we're going to multiply that, and pardon the lack of space here. For every 1 mole calcium nitrate, we have 2 moles of nitrate. Now, where am I getting that 2 from? From my balanced equation, right? So I'm using a stoichiometric ratio to answer this problem. And if we do this math, 0.05 molar nitrate. Okay? So the trick to this is to write the equation where we split calcium nitrate into its respective ions. All right, question 7. So how much heat is released when 4.5 grams of methane is burned? So it gives us a balanced chemical equation. It's always important to check to make sure that your equation is balanced. And then the next thing to look at is, what is this equation telling us? Well, this equation is telling us that if we have 1 mole of methane, right, if we have 1 mole of methane and we burn it, we make that much heat, right? So the question is, do we have 1 mole of methane? Well, I don't know. We've got 4.5 grams. Is that 1 mole? Well, what we got to do is convert grams into moles, and then we've got to use our balanced equation to figure out how much heat is released from that. So step 1, grams into moles. How many times have we done that already this semester? So 16 grams of methane for every 1 mole of methane, right? And now, let me just switch colors here, right? Now we're going to use this ratio here, right? For every 1 mole of methane, right? For every 1 mole methane, we make, or we produce, or we release 890 kilojoules of energy. So this is part of our stoichiometric balanced equation, right? In this equation, this example that we're doing, the balanced equation only has 1 mole of methane. If it was 2 or 3 or whatever, we'd have to change that appropriately. But in this case, it's just 1. And if we do this, I got it to be about 250 kilojoules. So grams into moles, and then in red, we use our stoichiometric ratio there to figure out how much heat is released from 4.5 grams. All right. Question 8. Calculate delta H. This is a Hess's Law problem, right? Remember, these kind of have a unique look to them, right? We're asked to figure out delta H, and then it gives us information about individual reactions. So we've got to add all these up down here to make that equation here, right? We've got to add up the individual components to make the overall reaction. So I don't know any magic tricks to work through these problems. Again, if I knew some magic, I would share it with you guys. All we can do is kind of, systematically work through these problems. So here's how I approach this. Remember, we need to basically find every component of this equation somewhere down here. So I just start, with one of these and see where I can find it. So nitrogen monoxide, NO. Well, there's only one equation down here that has nitrogen monoxide, and that's this guy right here. Let me just put a label here just so we can refer to colors. So in the overall equation in red, nitrogen monoxide is on the left of the arrow, right? It's on the left of the arrow. It's a reactant. Here, it's on the left of the arrow. It's a reactant also. So we don't need to change anything. There's one here and there's one here. So I'm going to start off with my assumption that we just need to leave that one in black the same. So I'm going to say multiply that by -1. Okay, moving on down. Now we look for our buddy oxygen. Just singular atomic oxygen, kind of strange. Now, in our red equation, oxygen's on the left of the arrow, and there's only one place where oxygen is, and it's down here on the right. Now, if you look at it, right, so we know that we need to flip our purple equation, right? We need to flip our purple equation so it looks the same as, right? So we get the oxygen on the right side there, on the correct side, I should say, on the correct side. But also take a look at the stoichiometry. Here it's 2, here it's 1, right? There's just 1 there. So what we need to do is not only multiply by negative to flip it, we need to multiply by a -1/2 so that we get the correct stoichiometry. All right, so we're done with that. NO2. NO2 is on the right side of the arrow. Here's NO2, it's on the right side of the arrow. The stoichiometry is the same, it's 1 and 1 in both cases, so it doesn't look like we need to do anything to that. And you say, oh, okay, so multiply the equation in black by 1, the equation in purple by -1/2. You say, well, what about that equation in the middle? Well, we'll see what's going to happen to that in just a minute here, okay? So let's write out what we have so far, right? Let's write out what we have in the black and in the purple. In the black, we have NO plus O3, right? In the purple, we have, I'm going ahead and adding in my equation over here, right? The -1/2. So if we multiply the purple by -1/2, right, we would get plus O, right? That's everything on the left side of the arrow. Oops, I meant to put that in purple, just so we're tracking where everything came from. All right. Let's write out the other stuff. NO2 plus O2 plus 1/2 O2. So if you pause, take a look at what I did. I just pulled everything. Let me do this in blue. I pulled everything from here and here, right, to put it here. And I pulled, I'm running out of colors, so bear with me here, right? I pulled everything from here and here and put it here. And I just wrote out what we've done so far, okay? Now you see what the issue is, right? The issue that kind of cropped up is we've got O2s here, right? We've got 3/2 O2, but we don't have 3/2 O2 anywhere in here, so we have to get rid of that somehow. So how can we get rid of 3/2 O2? Well, there it is, right over here. In our current answer, our 3 halves O2 is on the right side. Here it's on the right side, but to cancel it out, we're going to have to get that to the opposite side. So what we're going to need to do in this case is multiply this guy by -1 to flip it around. Okay? So what I'm going to do is take this equation here. I'm going to duplicate it, right? I'm basically going to rewrite it. And I'm going to add in my factors in green, right? I'm going to add in my factors in green. Let me just move it over here real quick. Give myself some space, right? So now that we know what we want to do with the green, we have 3 halves O2, right? Plus the rest of this stuff, plus O3 over here. So that was kind of tricky. So let me pause here and just kind of see if I can walk you back through what I did. I added my black and my purple equation together to get this guy, right? I looked at my green starred reaction and saw that O2 was present in here, but it wasn't present anywhere in my overall equation. And to cancel it out, I went here and I flipped that around to cancel out my O2. So let's see what happens now. Let me do this in red. O3, right, cancels out with O3 over here. Good. O2 plus 1/2 O2 is 3 halves O2. So 3 halves O2 cancels out with 3 halves O2. If we erase everything we crossed out, there's that, right? There's that. That's crossed out, right? All this. What do we have left over? NO plus O goes to make NO2, which is exactly the same as what we want up there. Excellent. Now that we've got the correct, let's say, adjustment factors, right? These guys over here, right? Now that we've got the correct adjustment factors, now we actually need to go through and figure out delta H. And for this, all we're going to do is look at what we did to the equation. We multiplied the black equation by 1, so we just bring over the -198. We flipped the green reaction, so -142 becomes plus 142.3. Plus 495 times -1/2, right, becomes basically 495, right, divided by 2. And if we add all this together, I got delta H is equal to -304.1 kilojoules, right? So if we just add all these equations, or excuse me, not equations, if we add all those numbers together, I got -304. So what can I say about Hess's law? Hess's law, you got to approach it systematically. Find one piece at a time, and don't forget, right? Don't forget to come back and do your delta H at the end of your work. All right, I'm going to zoom out so you guys can see everything in here. And that is the end of quiz 6.